Cool. Thank Luca for the introduction just now. And thank the organizers for inviting me to share some of the work we had at SNAP. I know currently there is another very, very hot topic going on in the other room. So I really appreciate people who are still staying here, staying with me. And I hope you can enjoy this talk. So the title of the talk today is From Challenges to Solutions, a Causal Inference Perspective on Mobile App Measurement at SNAP. So SNAP is the parent company of Snapchat. Snapchat is a mobile app that is pretty popular among young people, especially teenagers. If maybe some of you also use it, hopefully. And there are 5 core tabs in Snapchat, including map, communication, camera, stories, and a spotlight. So in the past few years, one of the key research areas of my team worked on was about the measuring methodologies of mobile apps. And the goal of this is to help the improvement of the performance and the usage of Snapchat. So why do we work on this area, and why causal inference for measurement? This is because in order to gain actionable insights, such as understanding and measuring the impact of app development on user engagement, we should rely on causal inference. And we all know that correlation does not imply causation. So the reason is that the essence of causal inference lies in counterfactual reasoning. Causal effect essentially is the difference in outcomes between 2 scenarios and all else being equal. What does all else being equal mean? This is the idea of having parallel universes. So imagine that we have a population. In universe A, this population receives some treatment, which is some discount here. And then we measure the outcome is some revenue of $120. And for the same population in universe B, they don't receive the treatment. Basically, there is no discount. And then we measure that the revenue is $100. And then we can conclude that the difference caused by this treatment is $20. And in this talk, we will focus on the following 3 challenges of doing causal inference for online measurement for mobile apps. The first one is beyond randomization, which means when randomization control trials are not feasible anymore. Because we know that for most causal inference in industry, A/B testing is the widely used method. But there are scenarios when randomization is not feasible. And the second topic is about beyond average. This is when we know that the most commonly used measurement effect is called average treatment effect. But there are good cases that average treatment effect cannot provide us enough insights. And the third topic is about beyond guardrail. That is when the app performance metrics surpass their role of guardrails and become the focus of our analysis. So these scenarios pose challenges for online measurement in mobile apps. And in this talk, we will also show how we provide solutions to these challenges at SNAP. Okay, so now let's take a look at the first part, which is beyond randomization. And we will show how we provide a scalable observational causal inference tool at SNAP. As we mentioned before, that A/B testing is the most widely used approach in industry and are often considered as the gold standard. But they are not always feasible because sometimes we cannot randomize users who are impacted versus who are not. So for example, we cannot intentionally degrade app performance or increase app crashes to assess their impact on user engagement. And most marketing campaigns, for most marketing campaigns, we cannot randomize users. As users, they are more likely to be exposed to the campaigns, could be because of reasons such as they live near to a billboard or they are from some high school. And also some effects from exogenous shocks or external shocks, such as shocks from some carrier throttling or some external policies can also impact users, but we cannot really randomize users who got impacted versus not. Furthermore, even for scenarios when we can run A/B tests, reasons such as having network effect or we want to measure the long-term effect can also make A/B tests not the best choice for us. So because of these reasons, observational causal inference is in need. Observational causal inference is a collection of methods to estimate treatment effects when the treatment is observed rather than being randomly assigned. So here is a figure roughly explains the relationship between experimental causal inference and observational causal inference. So at the very top, the experimental causal inference, or A/B testing, usually it has the highest accuracy in measurement, but also it has the highest cost. In contrast, correlation, it usually has the lowest cost, but it also has the lowest accuracy. And we know a lot of data science and machine learning tasks are usually, such as prediction, are usually in this category. And in the middle is the observational causal inference. It compromises methods to estimate treatment effect when the treatment is observed rather than randomly assigned. And in industry, we find the biggest challenges of applying causal inference are scalability and democratization. So why are these challenges in industry? This is because, first of all, we know although there are a lot of data science-friendly packages in R or Python available for us to do observational causal inference analysis, but usually ad hoc analysis has a higher risk of leading to inconsistent or even misleading results. Just imagine the scenario that if tech companies will run randomized control experiments without having any experimentation platform. So the second challenge is scalability, because we know most observational causal inference methods, they come from econometrics. And usually most of them can only handle small data set, which leads to high variance and high bias. And they are not really designed, not feasible to handle large data set we have in industry. So because of these reasons, building scalable tools or platforms for observational causal inference in industry is not a trivial problem. So at Snap, we built a scalable synthetic control tool to deal with this, basically for large observational causal inference analysis. And this paper is accepted at KDD this year, and you are very welcome to check it out. So what is synthetic control? Unlike A/B testing, we know A/B testing utilizes randomization to construct the control group in the treatment group. But for synthetic control, we first choose a cohort of users who are not exposed to the treatment as the control donor pool. And then we assign a weight to each user or each data unit in the control donor pool so that the synthetic control group matches with the treatment group in the selected attributes or pre-treatment features. So let's take a look at this example. In the figure on the left-hand side, it shows the cigarette sales in California and other states from 1970s to 2000. And what happened in 1988 was there was California passed Proposition 99, which was a regulation about the sale tax of cigarette, and they increased the sale tax of cigarettes significantly. And in order to measure the impact of Proposition 99 on the sales of cigarettes in California, if we just look at the figure on the left-hand side, it's very hard to tell because we see that sales of cigarettes was already started declining as early as 1970s, and the sales in other states, they were also declining. So what we do is we construct the synthetic control group by using the data from other states as the control donor pool. And then we put weight to the data and then try to match that group, their pre-treatment trend with the sales in California. So we see these two curves, they are very identical before the treatment happens. And then we are able to measure the difference of the sales in California versus the sales in the synthetic control group. And the difference basically tells us the causal impact of Proposition 99 on the sales of cigarette in California. So this is the rough idea of synthetic control. So now we see that the key of synthetic control is how to assign the weights to the data in the control donor pool. In econometrics, there are two very recent and also widely used approaches to do that called entropy balancing and microsinks. And based on these two approaches, we innovate two distributed computing algorithms. One called distributed entropy balancing and the other one called distributed microsinks. We use them as our balancing approaches. And then we use MapReduce framework to calculate the gradient of Lagrange multiply and apply iterative gradient-based solvers. And our algorithm is able to scale linearly with the number of data points and number of covariates. And we show that it can be scaled up to more than 100 million data points and 1,000 we in our experiment. So by our simulation and experiment, we see that on a single node machine, our algorithm runs faster than Google's empirical calibration package and the Meta's balance package. And on Dataproc, the running time of our approaches is less than 10 minutes for a causal analysis with a data set of over 10 million users. So here are the key takeaways of the first part. So first of all, we know that causal inference is a critical area of data science and machine learning in industry in general. And as we quoted here from an article from Harvard Business Review, that observational causal inference can really extend our abilities to uncover strategic opportunities, inform business intuitions, etc. So in order to having observational causal inference in industry, scalability and the democratizations are two challenges of applying observational causal inference in our day-to-day measurement. And at Snap, we have some scalable balancing approaches called distributed entropy balancing and the distributed microsinks provide some solutions to these challenges. All right. Now let's move on to the second part, which is beyond average. As we mentioned before that, the most commonly used estimation is called average treatment effect. But there are many cases, many scenarios in industry that average treatment effect cannot provide us with enough insights anymore. So what we do at Snap is we had a couple of frameworks for heterogeneous treatment effect. And now I'm showing how we are dealing with these with heterogeneous treatment effect. So before we talk about heterogeneous treatment effect, let's first take a look what is average treatment effect. Average treatment effect measures the difference in the mean outcomes between units assigned to the treatment and the units assigned to the control. So in this equation, Z is the treatment. So then when Z is 0, the first part basically gives the expected average mean outcome of the units in treatment. And similarly, the second part is when there is no treatment, we get the expected average mean outcome of the units without treatment. And then their difference is called the average treatment effect. That's very simple. So then why beyond average? This is because there are many factors can contribute to the heterogeneity of mobile app data. So for example, mobile app users, they are highly heterogeneous. Users could come from different countries, of different age groups, of different genders, and also like their different engagement with the app. And also many mobile apps, they are multifunctional, so that users' intents of using the app vary a lot as well. So taking Snapchat as an example again, Snapchat has the function of camera, communication, or social media. So users, they use Snapchat maybe for very different purposes. Furthermore, there are thousands of mobile app devices, mobile device types on the market. We know like iOS, Android, but even just for Android, Snapchat user base has several thousand of different Android mobile devices. So they're highly different from each other. And what is more is like, when users, they use their mobile apps, they could be in very different environments. They could be in the environment of having Wi-Fi, or in the environment in some data plans, but with various mobile carriers worldwide. So all these factors could contribute to the heterogeneity of the mobile app data. So when the population has very high heterogeneity, the average treatment effect cannot really provide us with the best insights anymore, such as shown on the left figure. So instead, we should first break down the populations into different cohorts or different subgroups based on some dimension, such as users' countries, their device types, etc., and then examine the heterogeneous responses of these subgroups to the treatment. So this is called the HTE. So then what's the challenges about HTE in industry? First of all, there are many different ways to do the breakdown actually. So we see that could be like countries, age groups, engagement history of the users, device types. So before we do the breakdown, we may not know like which breakdown actually is the best breakdown for us to find the most heterogeneous effects. And the traditional way of HTE breakdown in industry could be cumbersome and subject to bias. As data science, they may choose arbitrary breakdowns manually, and it can also cost a lot of effort and time. So then we propose a systematic paradigm for HTE detection, surfacing, and characterization. This piece of work was published at CODE, or the Conference on Digital Experimentation at MIT last year. So in this systematic paradigm, instead of like doing ad hoc HTE analysis, what we propose is we follow these 3 steps in getting the insights about the HTE. So the first step is to answer the question, is there heterogeneity in the treatment effects? So this is the global test to determine if whether there is HTE present before specifying into any breakdowns. And the second step is, if there is heterogeneity in the treatment effect, then which subgroup breakdowns are most important in explaining this HTE? So what we have is we systematically measure how much variation can be explained by known breakdowns. And finally, we answer the question, how do treatment effect vary beyond the conditional mean? And we model individual treatment effects as a mixture of conditional distribution to answer this question. So let's first take a look at the way we answer the first question, detection. So the intuition behind detection is, if there, under the now of no variation in the treatment effect, the variance of treatment outcomes and the control outcomes should be the same. That is, in another word, the treatment outcomes should be just a constant shift of the control outcome. So when the treatment effect varies, then we know the treatment effect variance is an additional source of variable that will typically increase the overall treatment effect outcome variance. And we use this to construct the hypothesis test for HTE detection. And we tried 3 different approaches or 3 tests to do the global test, including Bootstrap F test, Kurtosis log variance test, Fisher's randomization test. And based on our simulation, we see that the kurtosis-based log variance test is able to detect HTE with the smallest power among all these 3 approaches. And it is computationally efficient and fully sequelizable. And for the second step, to answer the surfacing question, what we do is we want to construct an R-square, which is measure that corresponds to how much the treatment effect variation, or TEV, can be explained by the breakdown. And then we compare R-square of each different ways of breakdown and see which one has the highest R-square value. And to estimate the explained TEV, we can look at the variance of the conditional average treatment effect. And we also can derive sensible bounds for idiosyncratic TEV and further narrow down the bounds by making reasonable assumptions. And finally, the characterization step. So after we identify the breakdown that best explains the HTE from the previous step, in the third step, we surface the conditional ITE distribution for every strata from that breakdown. And then we visualize the global ITE distribution as the weighted mixture of these empirical distributions with each strata. And taking this example, the gray shade is the global ITE distribution. And these colored shades are the distributions of IT distribution in each strata. And from this example, we can see that most of the tail treatment effects come from the strata 7, which means that users who benefit the most from the treatment are most likely from strata 7 users. Okay, So now after we take a look at how we deal with this HTE like in a very systematic paradigm, another challenge we want to talk about here is dealing with the multiple testing problem. So what is multiple testing problem? Here is like a cartoon example. So assume that you usually have acne one day in a month. And in order to understand, to know like what causes acne, you take jelly beans of one different color each day in a month. And on the day when you take green jelly beans, you had acne. So then you conclude that, oh, green jelly beans link to acne with this statistical significance. So this is the multiple testing problem, because even there is no actual link between acne and the green jelly beans, but the way you test it can show links with statistical significance. So this problem, multiple testing problem, is also prevalent in HTE, because when we do breakdowns, there are many possible ways to do it, and after you test maybe like 100 subgroups, and probably you are always able to find some subgroups showing static. So in order to deal with this multiple testing problem in HTE, we propose in the prototype a statistical framework based on two methods for HTE detection while controlling false discovery rate from multiple testing. And this work was published also at KDD in 2018. So in this framework, we first use transform outcome to calculate the HTE detection. So from a paper by Susan S. and Ibens in 2015, they conclude that the average of transform outcome for a subgroup is the ATE for that subgroup. And then we use two false discovery rate control methods for the multiple testing problem. One is called knockoff method, and the other is called Benjamini-Hochberg method. So our simulation results show that shows that knockoff method tend to have smaller average FDR when it is difficult to detect the treatment effect, and it has wider applications in detecting HTE. But on the other hand, the Benjamini-Hochberg method is easier and faster to implement. And when we try this method on real data, we see they're able to give us pretty consistent and good results overall. Okay, so the key takeaways from this part, the second part, is about heterogeneous treatment effect are the following. First of all, we have a systematic paradigm for HTE to avoid ad hoc breakdowns. And in this paradigm, we have 3 steps. The first one is detection, the second one is surfacing, and the third one is characterization. And with these 3 steps, we can avoid ad hoc analysis of HTE breakdown. And the second is we should have FDR control for HTE to deal with the multiple testing problem. As multiple testing problem is prevalent in HTE, and we propose using 2 false discovery rate control methods, such as knockoff method and Benjamini-Hochberg method in HTE. Okay, so after we take after this second part, now let's take a look at the third part, which is called beyond guardrail. So in this part, what we look at is we talk about when at performance metrics, they surpass the role of being guardrail and become the focus of our analysis. And I will show our research on tackling with some of the challenges when we measuring app performance and analyzing performance metrics. So first of all, let's take a look at what are performance metrics. Performance metrics, generally speaking, they are quantitative measurements used to assess the performance and the effectiveness of an app. So for example, such as like app response time, or app load time, or like camera latency, sending latency time. These are all considered as app performance metrics. Then what is guardrail? So in most online experiments for traditional online services, such as search engine, performance metrics are used as guardrail metrics mostly, as we use them to help to make sure that some important dimensions that are not captured by user engagement metrics are not going in the wrong way. So that's the traditional usage of performance metrics in online services. However, nowadays, as we have in the area of like mobile apps, for many multifunctional mobile apps, we need to put app performance improvements really in the focus in order to drive user engagement. So this is the key the reason that why now we need to focus on performance metrics, and it's much important than before. So taking an example from Snapchat. So we know that in late 2017, there was a large engineering initiative to rewrite the Android version of Snapchat for faster performance. Basically, this was an initiative to, as we want to retain and attract more Snapchat users, especially Android users. And after this rebuild, we find this new Android Snapchat app opens 20% faster on average and result in a 6% increase in the number of people sending snaps from some of the lowest performing devices in the first week. So this is really significant for the company. So then the question is like, as we put performance metrics in our focus, then what's special about it? So unlike user engagement metrics, for which one user usually has one data point, one user could have either 0, 1, or even more than one data points in a performance metric. So for example, if user A opens Snapchat for 10 times during the experiment, and then user A has 10 data point or event of app open latency metric. On the other hand, if a user B does not open Snapchat at all during this time of experiment, then user B has 0 data point of app open latency. So the current industry standard for measuring performance metric is construct event level performance metric by tracking a representative percentile, such as 50 or 90th percentile over all events in either the control or treatment group, irrespective of the users that the event comes from. So then this causes a problem. The first problem is called NonID. As usually we assume that the data points of mobile users are ID. But since one user could have more than one data point, then for a performance metric, then the data points of the performance metrics are not ID anymore. So then the questions are like, what is the best summary statistics to represent the performance metrics, and how to accurately estimate the variance of non-ID sample data point at scale in this case? And the second challenge of performance metric is performance metric, there are two major types of heterogeneity for performance metrics. The first one is the user engagement are highly skewed. So taking this example, 80% less engaged users, they contribute to about 25% total events in the performance metric. And the 20% highest engaged users, they contribute to 75% of the events in the performance metric. And the second is the mobile devices, they are highly heterogeneous, as we mentioned before. And the performance of these devices of higher-end device versus lower-end device could vary a lot. So then the questions are how not to put the majority less engaged users into the blind spot of our measurement, and how to deal with the vast heterogeneity of mobile devices. And the third challenge about performance metric is self-selection bias. So we mentioned before that if a user never uses certain function, then the user doesn't have any data point in this performance metric. For example, if a user does not use Snapchat camera to create any image during an experiment, then we do not have the camera latency metric for this user. So in A/B testing or like causal inference, if there are different number of users having no camera latency metric in the control and treatment, then the user counts of the performance metric camera latency are biased between these two groups. So this essentially is a missing data problem. And unlike most user engagement metric that can be imputed by 0 when the user does not have any event for that metric, we cannot do the same for the performance metrics. So then the question is how to deal with this missing data problem, because its consequence could be invalid metric results. So in the past, we had some research around these challenges, and our work on the solutions to these issues, such as NonID, heterogeneity, and the missing data problem, the performance metrics, the research was published in 2 papers at Wisdom in 2021. And now I will show some of the solutions we have from this shown in this paper. So first of all, we mentioned before that when we measure performance metrics, we usually use event level. But now let's see, what about we use user level performance metrics? So user level performance metric is we first compute a quantile value for each user over all their events, and then average this value over all users so that all users have equal weights. And for the good thing about user level performance metric is they treat every user equally, so they can better capture the experience of all users rather than being biased toward heavy users, as we see in the event level metric. And for the missing data problem, or self-selection bias, we propose 2 approaches to deal with it. The first approach is called imputation. So for imputation, first of all, we identify all the users with observed metric in both control and the treatment group. And then we impute the rest of the users based on the features of these observed users and impute their metric value. And then we are able to compare the performance metric in the control and the treatment group this way. And for the second approach is called matching method. So in this method, similarly, we first identify users with observed metrics. And then we match these users by giving them weights. and then compare the weighted metrics in control and the treatment. And our simulation results are showing that they are shows that they have like reasonably good results in dealing with this missing data problem. So in these figures, we see that probably it's not very obvious, but there is like a purple dashed line in each figure. This is the true ATE, or we can consider as the ground truth. And the black line is the result without any correction, so basically with the missing data problem. And we see that as the missing data problem gets bigger, then the result from this without correction method, it deviates from the true ATE significantly. But on the other hand, the green and the red lines are the results of by matching and imputation. And we see that they are showing pretty good approximation to the ground truth. Okay, and in addition, we also propose a metric measurement called continuous quantile. So as we mentioned before, the industry standard for performance metric is to measure the quantile treatment effect on event level, and most commonly at P50 and P90s. So, but however, P50 or P90s are sometimes not able to give us the whole picture about the treatment effect in an experiment. Taking this like real example, we see that even in one single experiment, P50 and P90 could give opposite directions for the same performance metric. So why is that? This is because performance metrics, they are essentially distributions of performance events. So they can be summarized in many other ways than just P50 and P90. So in this work, we proposed a method called CONC, or continuous quantile treatment effects, to measure performance metrics in online control experiments. So this is a scalable and theoretically sound method that can provide QTE with percentage delta of p-values and confidence intervals at arbitrary range of quantile locations simultaneously. And it circumvents the issue of density estimation bandwidth choice altogether, and improve the accuracy of delta method by log transformation for percentage changes. And our validation of this method on online experiments at SNAP show very consistent results with existing P50 and P90s, and also has pretty stable performance. So this figure shows that CONC, or continuous quantile, provides a full picture of the treatment effect of a performance metric. Instead of just looking at P50 or P90, it ranged the entire spectrum of the quantile level. And from this picture, we can see clearly that there is strong heterogeneity of the treatment effect, as there is negative effect or red shades at the lower quantile level, while positive effect on the higher quantile level. Okay, so after we take a look at the previous three challenges, there actually is another bonus challenge for performance metric, which is about the causation of performance metric with user engagement. This is because we know a performance change could have dramatic impact on user engagement. Then the question is how to establish the causal relationship between performance change and user engagement. And this will really help our developers, app developers, to optimize our resources and to drive the best user engagement from app development. A/B testing, we know it usually gives us the best causal inference result, but slowing down app performance to evaluate its impact on user engagement can potentially hurt user experience. And also it's really not very practical for us to run a lot of A/B tests to measure numerous performance metrics of our interests. So we have a solution here. So remember, in the first part, we talked about the observational causal inference. So the solution here is we utilize observational data on users who naturally experience week-over-week app performance regression, and utilize this in data in our scalable synthetic control framework to estimate the causal impact of app performance on user engagement. So in this approach, what we do is, first we choose the users whose week-over-week performance metric change are relatively stable as the users in the control group, and the users who experience some week-over-week performance regression as users in the treatment group. And this threshold could vary based on the metric of your choice. And then we apply synthetic control to make the control and treatment group comparable. And in order to do this, we choose core user engagement metrics and user attributes as the covariates. And we use the first to 18 weeks of data as the week to match these two groups, and week 19 and 20 as the validation period. And starting from week 21st, this is when the performance regression naturally happens. We also borrow the concept of elasticity from econometric to standardize the impact of 1% of performance metric regression on user engagement. And our analysis showed that there is consistent negative elasticity, which suggests that slower latency causes decrease of user engagement. And we also see heterogeneity as if we break down the elasticity by performance or engagement, they're showing heterogeneity there. Okay, so the key takeaways of this part is, first of all, we see that accurately measuring and summarizing performance metric is not a trivial problem given the following challenges, including non-ID, high heterogeneity, and the missing data problem. And we provide some solutions to these challenges as we summarize performance metrics on user level versus event level. We use imputation matching to correct self-selection bias. And we also have the continuous quantile method to show the heterogeneity and measure the performance metrics of the full spectrum. And the bonus challenge we deal with is we have a scalable method to measure the causal relationship of app performance on user engagement. Okay, so here is the summary of the talk. In this talk, we presented 3 challenges of using causal inference for mobile app measurement. These challenges include beyond randomization, beyond average, and beyond guardrail. And we provide solutions to these challenges as we have a scalable observational causal inference tool to deal with for observational causal inference analysis. And we have 2 frameworks for heterogeneous treatment effect when average treatment effect is cannot provide us with enough insights. And finally, we have some research to tackle with challenges of measuring app performance metrics. if you are interested, you can also take a look at the references I quoted in this talk. And yeah, thank you so much for staying with me. And now I'm taking some questions.